Alright, so today we're going to actually finish up U substitution. For trig functions, logarithms, and exponential functions. Okay, so if we know that the integral of sine of x dx is equal to negative cosine of x plus c, then that means the integral of sine of u du is equal to negative cosine of u plus c. So all the derivatives we had before is the exact same, it's just the x's are changing to u's. Okay, so that means the integral of cosine of u with respect to u is equal to sine of u plus c. The integral of cotangent of u, wrong parentheses, don't need that, is equal to negative natural log of cosine of u, absolute value, plus c. The integral of tangent of u is equal to the natural log of absolute value of sine. Oh, that's the other way around. This should be sine, this should be cosine. Of u plus c. Okay, so most of the time you're just going to use these two, but those two will, the other will kind of creep around every here and there. Okay, we also have the integral of du over u is equal to the natural log of the absolute value of u plus c. We have the integral of e to the u du is equal to e to the u plus c. We have the integral of a to the power of u du, which is equal to a to the u over natural log of a plus c. And our logarithm, the integral of log base a. In this case, it's t because they really didn't have any u values there. So you can put u, actually we'll put u, just in case, because you can always equal t.
Is it element in natural?
Yep, natural log.
Natural log
of a.
0 or a?
Yep, a. Did I make that look like a 0? I think it might just be catching them. Yep, there you go. Oh, no problem. Actually, you can turn that to u.
I just want to make sure it's good.
Oh, not a problem. The u is equal to u times natural log of u minus 1 all over natural log of a plus c. For most of the problems, these are either t or x, so you really don't need the u, but just put it there anyway. Okay. Now these two are going to require sometimes a lot of manipulation. So we're going to do a few examples of those. The sine and cosine ones aren't too bad. All right, leave that up there for a few. right, so for our first example, bring that down a little bit. Say if we have the integral of negative 11 times t to the 7th power times cosine of t to the 8th power with respect to t. Okay. So the goal here is to kind of get rid of everything else and make that just cosine of u. Okay, so the first thing we want to do is we want to let u equals t to the 8th power. That's the only way we're going to get cosine of u. Okay, so if we have u, bless you, equals t to the 8th power, that means our derivative of u is going to be 8t to the 7th with respect to t. And if we divide both sides by 8, our du over 8 is equal to t to the 7th with respect to t. All right, so we go back to our problem. We just go ahead and bring that negative 11 out. So we have negative 11 times the integral. And those two, I'm just going to switch them up just so they'll match up everything. So that's cosine t to the power of 8 times t to the 7th with respect to t. Okay. So just like before, this gives us our cosine of u. And this gives us our du over 8. Okay, so we end up with negative 11 times the integral, we'll make that a little, there we go, cosine of u times du over 8. And at 8, we can just factor it right on out. So we have negative 11 over 8 times the integral of cosine of u du. Which gives us negative 11 over 8 sine of u plus c. So the only thing left is just to replace our u. And we know that our u is t to the 8th. So we have negative 11 over 8 sine of t to the 8th plus c. All right, so any questions on that one?
So that would be just the answer. They're not going to ask you to solve.
For some. We actually do have a few where we actually solve it. So this one's just integrating when they don't have the a and b values. All right, any other questions on this one? All right. Okay, so for our next example, we have the integral of negative 17 t to the 4th cosine t to the 5th. Oh, did I just use a cosine one? Was that a sine one? Yep, I already did a cosine one. I have to do the sine one. So change that to negative 12 sine. Didn't want to do two cosine ones in a row. So negative 12 x squared sine of x to the 3rd dx. So just like before, our goal is to get this to become sine u du. Okay, so we do that by making u equal x to the third power, which means your derivative of u equals 3x squared with respect to x. Divide both sides by 3. Du over 3 equals x squared with respect to x. Okay. So now we get that negative 12, and we go ahead and factor that out to the front. So you have negative 12 times the integral, and just switch around those two. Sine of x to the third, x squared with respect to x. Okay, so this gives us our sine of u, and this gives us our du over 3. Okay, so we end up with negative 12 times the integral of sine of u du over 3, and if we bring that 3 right on out, negative 12 over 3 times the integral of sine of u du. Okay, so if we go ahead and integrate that, negative 12 divided by 3, that's just negative 4. The integral of sine of u is negative cosine of u plus c. Okay. The negative and negative cancel each other out. So it's just 4 cosine of u plus c. Now all we have to do is replace our u. That gives us 4 cosine of x to the third plus c. So it's pretty much like the u substitution we did last class, but you're doing it with the trig functions now. All right. So any questions on that one? Okay.
So
Hmm?
the du to the third, that just means, with respect to u, correct? So
Yes.
where does the x squared, that just comes into as a fraction to the constant?
Which one are you on? Up here or down?
Right there.
Here.
Yeah, so
Mm-hmm.
I'm just curious, okay, it's just like factoring it out? Is that essentially what it is?
Oh, this part here, or
The x squared.
oh, the x squared? Oh, all we did was get it from the original problem, and instead of x squared times sine x to the third, we just switched them around. So when we got that, and really don't have to do that, it's just visually it makes it easier.
No, I understand that.
Oh, okay.
I'm not arguing with that.
Oh, okay.
What I'm asking is where'd it go? The x
Oh, where'd it go?
Like-
Oh, we just replaced x squared dx with that. That's why
Right.
the x squared dx turned into that.
Du just means with respect.
Yep, with respect to u. But it's
So-
1 over 3 times du.
Okay, so it just basically the x squared turned into 1/3. And
Yep,
you're taking
1/3
that-
du.
And then you're taking that out,
Hmm.
and all it says is just respect to du, basically. Am I right or no? I guess I'm still not understanding why the variable just went away.
Oh, you mean when we integrate, why it went away?
Yeah.
I'm trying to think of the best way to get this one. So with that one, if you remember how we would have like the power rule? You had like the integral of x to the n with respect to x.
Yes.
All that's telling us is that's the variable we're going to integrate. So when you have your du, they're just telling us we're going to integrate the u
And I
term.
understand that.
Mhm.
That's why I'm confused, is because of you're turning an x to the power of 2 into
Mhm.
du that is,
Oh, we're just swapping one equivalent value for another.
okay.
So if you remember the differentials, where we had the differential of x, I'll put that down here, equals f prime of x, oh, dy, sorry about that, equals f prime of x dx.
Mhm.
This is really the same thing. But instead, we're just using u instead of y.
Okay.
Does that make sense?
Kind of?
Yeah.
So, kind of feeding off from what he was saying,
Mm-hmm.
in the terms of an integral
Mm-hmm.
and how we end with dx, could that also be viewed as multiplying by the derivative of x, which is like multiplying by 1? So
If you remember, your dx is really just your delta x.
Right.
So if you have your delta x, if you have delta x or delta y, it's still being multiplied by it. Because remember with the rectangles, you have all of your rectangles, you're multiplying all of those so you have, let's say, n number of rectangles. Then you're getting 1 times 1. So you're getting all those, I'm trying to visualize the best way possible. So you're getting this function, which is your f of x, and you're multiplying it by the number of rectangles. Because you have your first rectangle, your second one, your third one. Those are all the ones you're adding together.
Okay.
So that dx is kind of like your, like I said, it was formerly delta x.
Right.
But since your delta x is just now read as respect to x, because it's along the x-axis. Does that make a little clearer?
Right.
Okay.
But it seems that we also have derivative of u being brought in.
Well, the only reason we did u is kind of what they call a dummy variable.
Yeah.
And the only reason we do that is because we wanted to take something this complicated and make it familiar.
Right.
So the way we do that is say, okay, sometimes you'll see them use ds. They'll just pick any variable at all just to make it familiar. So if we were able to manipulate this and make it familiar, it'll make it a little easier to integrate. I don't know if that made any sense.
A little bit.
No. Oh, do you have a question?
No,
Oh,
I
okay.
got it.
Oh, you. No, okay. All right. Good. All right. So let's try another example. Okay, so let's say we have the integral of 17 cosine to the fourth of t sine of t with respect to t.
Cosine to the fourth?
Yep. Cosine to the fourth. Now, with problems like this, it helps to remember that cosine to the fourth of t is just cosine of t to the fourth power. It's just written a different way. Okay? So whenever you have this, we can let u equals cosine of t. Which means we can now have our derivative of u equal negative sine of t with respect to t. And just like we did before, we can multiply or divide, so we can make this negative 1 times our du equals sine of t with respect to t. Okay, so we have our u, and we have our